So a force is a push, a pull on an object. By exerting a force, you're pushing or you're pulling, lifting an object. And there are a couple special types of forces that apply on Earth and other places that are important to know about. One is friction. What is friction? Somebody tell me, Ryan?
Like two objects rubbing up against each other.
Okay. Okay, when two objects sort of rub against each other or are in contact with each other, they create friction. Friction is a force that resists motion. For example, if you have some hardwood floors or something in your house, if you're just wearing your socks and you run across the ground, you could probably slide over the floor. But if you try the same when you're wearing your sneakers, what happens? Yeah. You do not go sliding across the floor.
Maybe on your face.
What's the difference?
The friction.
Yeah, the difference is the amount of friction. Different types of surfaces have different amounts of friction that resist motion more than other objects. Okay? For example, if I have my water bottle here, and I put this piece of paper under it, is there some friction between my water bottle and the paper?
No.
There's no friction?
No, yes, there is.
There is. But if I pull this paper out,
You're a magician.
okay, my water bottle doesn't move.
Because you were pulling it with a force.
I was pulling with a strong force, okay, and this force was strong enough to overcome the friction between the water bottle and the paper. What if I apply a lower force? It moves with it. I'm not overcoming the force between the water bottle and the paper. Now, if I have this nasty green shag carpet from 1973, am I going to be able to yank this out?
No.
Are you guys ready?
No.
Form a protective barrier with your
Oh
hand.
my God.
Okay. So it stayed okay, but not great. It still moved significantly. What's the difference between this and a piece of paper?
There's more friction.
Friction, yeah. Much greater friction on the carpet than there is on the paper. Yes.
Can you still get to stand still with like as much force?
It depends on the object and the mass of the object. It depends on several factors. Okay, another special type of force that's important is gravity. Gravity is an attractive force between two objects. And there is a force of gravity between any two objects in the universe. For example, we are most familiar with gravity as it relates to the planet. So as you jump, why do you return back to the earth?
Gravity.
Force of gravity pulling you back down. But what you probably don't know is you are also exerting a force on the earth. Force of gravity causing earth to move toward you. So, but obviously the earth does not appreciably move. What's the difference? Why not? Why doesn't the earth move up and hit you in the feet?
Because the earth is so much bigger.
Yes, because gravity is dependent on mass, and the mass of the earth is exponentially more than the mass of you. Therefore, there's a much greater force attracting you to the earth than the earth to you. But there is an attraction between any two objects in the universe.
What about the moon?
Okay? Yep, same thing. All right. So let's talk about Newton's 3 laws. You're going to have to memorize them. You're going to have to know what they state in the proper order. So Newton's first law is called the law of inertia. Okay? The law of inertia is really pretty simple. It says that an object at rest will stay at rest. An object in motion will stay in motion. Unless, there's the unless part. So, what Newton's law says that if as I'm rolling on this little cart, I should continue rolling forever.
Where did you get that?
What is the unless part? So why don't I keep rolling forever? Thomas?
Because the force is stopping.
There is a force that's stopping me. In this case, what is that force?
Friction.
Friction. Okay, that force is friction, slows down my movement. Okay? But if there were a friction-free world, and I pushed against this, yes. If you've recently seen, there's a movie where this comes into play in the last, what? Gravity. In Gravity, what you see is the two characters in space, away from the Earth's gravitational pull. As they move, they get pushed off of the space station. What do they continue to do? Just go on forever. Okay? Because there's no gravity, there's also something else that's important. There's no friction, no air resistance either, and so they continue to move. Okay? And so an object in motion will stay in motion, an object at rest stays at rest unless acted upon by an outside force. So when I put my water bottle here, it's at rest, and it will tend to stay at rest. Okay? It wants to stay at rest. And so my force, okay, can overcome the friction, and it basically stays where it is. Okay? Inertia comes into play many, many times. For example, object at rest will stay at rest. That's the tablecloth trick. Because all the objects on the table want to stay there. This also comes into play, if you're in a car. Now, if you're in a car and your parents are driving, they're late to get you to school, so they're driving too fast. They don't see the car ahead of them, slowed down, and they have to hit the brakes very fast. What happens to you as a passenger? Nicholas?
You get jerked forward.
You go forward, right? When somebody jams the brakes, you go flying forward. And again, if you think about this in terms of inertia, when you're in the car traveling with your dad, going too fast,
No, it would be my mom.
okay? You are moving with the car at a high rate of speed. When the car starts to slow down quickly, what do you tend to do? Continue going forward. Okay? And that's why you go forward, right? Because the car slowed down, but your body's inertia causes you to continue forward, getting pressed against the seatbelt, if you're wearing one, hopefully, or it causes you to go forward into the dashboard. Same is true, so you're at the stoplight, okay, with your older brother, and they're trying to show off how fast they can go after the stoplight. When the light turns green and they hit the accelerator, what happens to you? Again, think of inertia. At the stoplight, you are at rest. Your body tends to stay at rest. But as the car starts moving forward very quickly, pushes against you, so the back of the seat's pushing against you, and that's why you sort of get pushed back. Okay, because your body was at rest. These are both because of inertia. You're riding your bike down the road, or your skateboard, and then you hit the curb.
Really?
Now, your skateboard stays at rest. What do you continue to do? Fly through the air because you were in motion and you continue in motion.
Is there any element or something that doesn't have any friction?
No. All right, so objects in motion tend to stay in motion. That's why this crash test dummy goes flying out of the car when it hits a barrier. This? No. I wouldn't think. No. All right. So, here we see some examples of friction. This motorcycle rider is in motion and continues in motion even though the motorcycle has stopped. This gentleman driving his convertible continues in motion.
Up and back again. Watch. He goes down. His feet are almost hitting the brake, and then he goes up and he goes down.
All right. Newton's second law.
Why do you have to start dirty?
Um, Newton's second law is one that involves a mathematical formula. So Newton's second law says the greater the mass of an object, the greater force it will take to accelerate that object. Now that's sort of common sense. The formula we have for Newton's second law is F equals ma. Force applied equals the mass of the object times the acceleration. No. So force equals mass times acceleration. So if someone were to exert a force on me, okay, they're exerting a force, I have a certain mass, and I would accelerate. However, if it were Mr. Arcuri staying on the scooter, the person would have to exert a much greater force to accelerate him at the same acceleration that they would need to accelerate me.
Why?
Because of his much greater mass. A cart full of groceries requires more force to accelerate than an empty cart. Okay? And also, the greater force you apply, the more the object will accelerate. What is mass times acceleration equal? Force. Yes. Get it? Star Wars physics.
That's so great.
I know, Ryan.
So funny. Does the second law like have a name like the law?
No, just Newton's second law.
Motion.
All right. So some examples. We have Mike and Bob here. Both ran out of gas. Mike seems to be driving a smaller car with a mass of 1,000 kilograms. He ran out of gas. So they need to push this car to the gas station. So, if he pushes on the car, he accelerates it to 0.05 meters per second squared. You can use Newton's law to figure out how much force Mike applied to his car. So I know I told you last week you should bring your calculator to class. So please take it out.
That was last week.
Should have had it, Lizzo.
So take it out. Again, when we solve these problems, we always follow the same set of steps. What is my first step?
What?
Write the formula. F equals ma in this case. Write down the formula. Substitute in our numbers. What numbers do we have?
1,000.
What is that? What is 1,000 what? That is what? 0.05 meters per second squared is the acceleration. Who has an answer? Dan?
50.
Okay. What do we get for a unit here? This is a challenge. Habib?
50 kilograms per meter per second.
Close, but
Squared. Squared.
close, but not quite. You said per, which means divide. Ryan?
50 kilograms per second.
No?
50 kilograms. 50 kilograms.
Yes. 50 kilograms meters per second squared. Luckily, though, we have an abbreviation for this unit. It is named after
Newton.
a famous physicist.
Newton.
Yes.
Why are you
The
writing
units are newtons, N. 50 newtons.
So kilograms times.
Yes, is 1 kilogram meter per second squared is equivalent to 1 Newton. He also invented the cookie with the fruity filling. Yeah. Fig Newton, yeah.
Wait, he invented those?
Yeah.
He didn't?
No.
So we did like the 8.
Alright. Now let's look at Bob. The math should be easier. Bob's van has a mass of 2,000 kilograms. He needs to push it back to the gas station as well. What force would he have to apply? Just using some mental skills, you should know. Brandon,
100
why did you say that?
Because 200 and 2,000 times 0.05 is 100.
Okay. Or you would know that the mass of the vehicle is twice as much, therefore he needs to exert twice the force to accelerate it.
So Bob is stronger?
Not necessarily. He exerted a greater force,
Yeah.
but maybe Mike just wasn't pushing as hard. So,
Oh.
Linda,
Why does Bob look like a girl?
why is he what?
Why does he look like a girl?
Men can have long hair as well. All right, so do we understand how to apply Newton's second law?
We do.
All right, Newton's third law. Newton's third law states that every action or every force has an equal and opposite reaction. Okay? For example, if I were here and I were to punch Jimmy in the face, okay, my fist would be exerting a force on Jimmy's face. Right? But Jimmy's face would be exerting an equal force on my fist in the opposite direction. Okay? So that's an equal and opposite force. Now, Jimmy's face would hurt a lot more than my hand because Jimmy's face is made of soft tissue, my hand is made of mostly bone. Okay? But the forces are equal. Okay? If I push off of Jimmy's chair here with a force, okay, I'm pushing on the chair with a certain force, but at the same time, there's an equal force pushing back on me, which causes me to roll across the floor. An equal and opposite force. Now, let me ask you this. If I step off of this and push on Jimmy's chair with the same force I just did, why? Why am I not moving? Yes. When I'm standing on the ground in my shoes, there's a much greater friction. The purpose of wheels is to do what? To reduce friction. Because when I'm standing in my shoes, the surface area between the rubber in my shoes and the floor is pretty significant. But if you think about a wheel, how much of the wheel is actually in contact with the ground? Just a tiny amount, right? Just a small amount because of the curve. Therefore, that less surface area means much less friction. Okay? You could also think about if you're ice skating. Ice is used because there's much less friction. Or if you're walking across and you hit a little patch of ice, your foot starts to slip because the friction of the surface has changed. You went from a concrete sidewalk where there's a lot of friction, you could walk, but all of a sudden, a patch of ice with much less friction, and so your foot slides on that surface and you fall. Rockets use Newton's third law to move. In a rocket, as high pressure exhaust is being shot out of one end of the rocket, there is an equal and opposite force pushing the rocket into the air. Okay? And so all of these things are important. That's what propels a rocket, this equal and opposite force. So
If you said like the wheels, it's like big, like the less friction, then there's the helium.
there's wheels, and so they reduce the friction so you can slide over the ground. If you think about it, if you're on a boat, or if you're on a canoe and you step out onto the dock, As you step out to jump on the dock, what happens to the boat? Yeah, it moves the opposite direction, right? And you follow the water. All right. Again, you're exerting an equal and opposite force. Thomas. Well, yeah, because you want some friction. If you had wheels made of ice, would they be good for propelling you across the road?
No.
Because as they turn, what would happen? There's too little friction, and therefore you just spin in place. So you want some amount of friction to propel you forward. And different types of cars, like have you ever seen race cars? What do the tires look like compared to tires on your parents' car?
They're smooth.
They're smooth. That is to reduce the amount of friction, okay, so they can come around their corner and sort of slide through those corners. But if you had those tires on your car at home, you'd be sliding around, they'd be poor in the winter. So again, you want a balance between friction. Yes. All right, so now Bob has a bright idea. He's sick of pushing his big van to the gas station. It's too hard. So he puts on his rollerblades. Figures he goes a lot faster with his rollerblades, he can push it while wearing his rollerblades. Smart idea?
No.
No, because what's going to happen to him?
They'll get pushed back.
Yes, he's going to get pushed backwards with an equal force that he pushed on, and the friction between his rollerblades and the ground is small, so he would move backwards.
What are those question mark beaters? Is there supposed to be a building for that?
Where?
On our,
No.
just like.
Oh, so you can figure out the force. Also, recoil on a gun. You know, if you play video games, if you go hunting or stuff, you know that if you shoot a gun,
Yeah.
there's a kickback, there is a force. The force of the bullet leaving the gun, there's an equal and opposite reaction, which puts a force on a person's shoulder or their hands if they're holding it. If you ever were holding, not a regular hose doesn't have a whole lot of force, but if you ever seen firefighters fighting a fire, how do they have to hold the fire hose? Very strongly, and sometimes multiple firefighters need to hold on to it because it's propelling so much water with such a great force that the opposite force would cause the hose to start flapping around. When you put a hole in a balloon, as air escapes the balloon, exerts a force that causes the balloon to go flying around the room. Then, well, Bob's not the most, he must not have taken science in junior high.
Oh.
All right, so let's summarize here.
Forgot about that.
So Newton's first law is the law of what?
Inertia.
Inertia. An object at rest stays at rest, an object in motion stays in motion. We have no formula for it. An example would just be a book sitting on your table. It stays there because there are no other forces acting upon it to cause it to move.
I just had objection in motion. Wait, what about the object in motion stays in motion, right?
Yeah, that's just sort of a brief summary. You should be able to remember.
What is the opposite force? Because
What's that?
you're applying the force to move the spool right now, right?
Yes, it's pushing against the ground. It prevents a force on the ground which pushes against me. Because I have low friction on the wheels, it causes me to move. All right, second law says the higher the mass, the harder it is to move an object. It does have a formula. What's the formula? F equals ma. Force equals mass times acceleration. Example would be that it takes a lot of force to push a heavy wheel. Law 3 states a reaction is an equal and opposite reaction. example, you pushing on a wall and the wall pushes back.
Is it supposed to say every action has an equal or opposite?
And opposite, really, is better way to say it. All right, this last thing. If you push against the wall, push it back. Every force equal and opposite. Don't worry about it. It's a video we'll watch tomorrow. All right, so another force that's interesting to talk about is centripetal force. Centripetal force is a force that keeps an object moving in a circle. So if you have an object you're swinging around, a yo-yo that you're swinging around, it continues in a circle because you're exerting a force keeping it moving in a circular pattern. Just like the moon orbiting around the earth, what's the force keeping it in a circular motion?
Gravity.
What happens if gravity shut off for a minute on the moon?
Probably.
It will continue moving in a straight line. Just like if you're winging around a yo-yo and you let go, you release that centripetal force, goes flying around. Okay? That's called centripetal force. Move in a straight line along the same path. Oh, I'll have to show you these two examples tomorrow.